Alright guys, every problem in the first video on solving trig equations was basically isolate the trig function, find the values for theta between 0 and 2 pi. A little bit of weirdness with tangent and cotangent in terms of not being redundant, and we're going to see more of that today. Alright, so we're just going to learn by doing 4 very particular examples. These 4 examples should hit on all of the details. So pay close attention and be careful that you don't just pay attention to procedures. Make sure that you're really listening to the finer points, because these 4 problems were picked very specifically so that in the least amount of examples I could teach anything and everything that might come up through other problems. So if there's anything I say or do that you're not clear about, those are the questions you want to ask. All right, here we go. All right, so the directions look very much the same. Find all values for theta living between 0 and 2 pi. And then we're going to write a general rule for the solutions, meaning capturing all solutions in terms of k, where k is an integer. All right, so the first thing you should notice is now we have sine of not theta, but sine of 2 theta. So that makes the problem interesting. We have the 2 theta. That's going to make this problem a little bit more challenging than just sine of theta equals 1/2. Now, just to be clear, this could be sine of 3 theta, same process, sine of 4 theta, sine of theta over 2. So lots of ways to kind of work this problem, but you do need to pay attention to the fact that we need the argument in this problem. So let me write this out. Sine of something to equal 1/2. That's my argument. Well, go to the unit circle. So we kind of start in the same place. Where does sine equal 1/2? So where is the height on the unit circle? Where is the y-coordinate on the unit circle? 1/2. And you know those two angles. Pi over 6 and 5 pi over 6. Okay, so here's where you start. 2 theta will either be pi over 6 or 2 theta will equal 5 pi over 6. Now I'm going to go ahead and write the general rule. All right, if I take pi over 6 and I add a multiple of 2 pi, I will be right back at the same terminal location, and my y-coordinate will still be 1/2. So these are my 2 general rules, right? But I want to know what theta is. We have to solve for theta. The goal is what values for theta will make this equation true. Okay, so I'm going to divide both sides of both general rules in this case by 2. So of course that gives me theta. Pi over 6 divided by 2 is pi over 12. 2 pi k divided by 2 is pi k. So this is one of my general rules. I'll call it theta 1. And then theta equals 5 pi over 12 plus pi k again. So I'll call this theta 2. You don't have to, but it's nice to know that there are 2 general rules. So I found my general rules, and my general rules are theta 1 and theta 2. Okay, so general rules found. Now, here's where you have to be careful. Now I want to find every single possible solution that lives between 0 and 2 pi. So here's where it gets interesting. Now you're going to actually plug in numbers for k. We haven't done this yet. We have had no need to. So now I'm going to take each one of these rules. So I'm going to take each rule, and I need theta to live between 0 and 2 pi. So let's see what happens. So first I'm going to see what happens when k is 0. So I have pi over 12 plus 0 times pi, which is 0. So one of my solutions, pi over 12, and of course pi over 12 is between 0 and 2 pi. So that's one of my solutions. Let's see what happens when k is 1. So I have pi over 12 plus pi times 1, which is pi. Now, this is a pattern we're going to see a lot. If I want pi to have a common denominator with pi over 12, then I'm going to rewrite that as 12 pi over 12. So I have pi over 12 plus 1 pi, which is 12 pi over 12 is 1 pi, which gives me 13 pi over 12. And we've seen that a lot, getting common denominators. Okay, so far, I have two solutions for the first general rule that live between 0 and 2 pi. Now, you could plug in 2 for pi, but what is 2 times pi? It's 2 pi. And 2 pi plus any positive number, of course, is going to be greater than 2 pi. We need theta to be less than 2 pi. So it's kind of, if your general rule involves pi k, not really difficult to see that plugging in 2 is going to get you outside of that range. You can plug it in and just kind of see that that happens. But for this general rule, we plugged in 0. We plugged in 1. If I were to plug in -1, I would end up with a negative angle. I need theta to be between 0 and 2 pi. So for this general rule, the only two angles I can get out of this equation, out of this rule formula, is when k is 0 and when k is 1. Those are two of my solutions. So now let's go to the second general rule and see, once again, I'm not going to plug in negative numbers. If I plugged in negative numbers for k, I would get negative angles. So the first number I'm going to plug in is 0 again, to get 5 pi over 12 plus pi times 0, which of course is just 5 pi over 12. Another distinct solution between 0 and 2 pi. So pi over 12, 5 pi over 12, 13 pi over 12. There is a nice numerical pattern here. 5 pi over 12. So now what if k is 1? So same pattern as before. Pi times 1 is pi. 12 pi over 12. So 5 pi over 12 plus, I'm going to rewrite pi in terms of a denominator with 12 on the, well, a fraction with 12 in the denominator. So I get 17 pi over 12. Fourth solution. So in this case, two general rules. When k is 0 and 1, I get my... So in this particular case, there are actually 4 distinct solutions between 0 and 2 pi. I wouldn't plug in 2 for k because 2 times pi is 2 pi. 2 pi plus an angle that's positive is going to be outside of the range we want to find. Okay? So you were asked to not only build a general rule, there were 2, but also find all solutions between 0 and 2 pi. In this case, there happen to be 4 solutions. Okay? As a general rule, let me go back to the original problem. When you see 2 theta, there will be twice as many solutions as there were in the more basic problems. If this were 3 theta, in general, there would be 6 solutions. And general pattern that has something to do with cutting angles in half, cutting angles in thirds. But you'll see that pattern as you practice. All right, on to the second example, which is example 7. So 9 total examples on solving trig equations. Okay, 1 through 5 were in the last video. We've seen 6. Now we're seeing 7. So, very similar to before, I want to know tangent of what equals 1. That's the question. Tangent of what equals 1. The argument has to go into the tangent function and come out as 1. Well, let's go to the unit circle. We know that tangent is 1 at pi over 4. So tangent of pi over 4 will give me y over x, which will give me a value of 1. And then the other solution is exactly pi away. There's that pattern at 5 pi over 4. I have negative root 2 over 2. Negative root 2 over 2 is that point. Y over x is 1. So I know that theta minus pi over 2, right, the argument must equal pi over 4 or 5 pi over 4. Now watch this. Pi over 4 plus pi k is my general rule. Now here's why there's only one general rule. If I say that the argument needs to be pi over 4 plus pi k, well, if k is 1, pi over 4 plus pi becomes 5 pi over 4. So this one general rule for tangent includes both options between 0 and 2 pi. All that to say, there are not two general rules for this tangent function, there's just one. Okay, so here's my general rule, but just like in the last problem, I can't just leave it as 2 theta. In this case, I can't just leave it as theta minus pi over 2. I have to solve for theta to build my general rule. So to solve for theta here, I need to add pi over 2 on both sides. So I'm going to add pi over 2 on both sides of the equation. Theta equals pi over 4 plus pi over 2 is 3 pi over 4 plus pi k. That is the one and only general rule in this problem. Now, since that's the only general rule, now all I have to do is plug in numbers for k. So let's plug in k equals 0 to find our first actual solution. So that gives me 3 pi over 4 plus pi times 0, which is just 3 pi over 4. Okay. So using the general rule, 3 pi over 4, if you plug 3 pi over 4 into this equation, it will be a true statement. Let's plug in k equals 1. So I have 3 pi over 4 plus pi times 1. So 3 pi over 4 plus pi, and just off to the side, pi is the same as 4 pi over 4. So I have 3 pi over 4 plus 4 pi over 4, which is 7 pi over 4. Second solution. Now you can see, once again, very similar for both problems. If I plug in 2 for k, I'm already outside of that range of 2 pi. So in this particular problem, there is one general rule. You've got to stop and think, what if I add pi times 1? Well, in this case, I would get the exact same general rule. And then there are two distinct solutions between 0 and 2 pi. All right, number 8 looks really basic, but here's where you got to be careful. This is me telling you pay attention to the directions, because on the next assessment, this problem looks really basic. And it kind of is. But you're going to build the general formula so that you can find all solutions, and then you're going to actually list 6 solutions. So you're not just going to find the angles, the solutions between 0 and 2 pi. You're going to find more than that. So you might find an angle that's close to 3 pi or 4 pi or 5 pi. So now we're kind of extending the directions to force you to better understand the problem. Okay, so to build the general formula, we need theta such that the y value is root 3 over 2. Okay, so there are 2 angles for theta where that happens. One is pi over 3, and the other one is 2 pi over 3. So I know in this particular problem that theta needs to be pi over 3 Okay, so the general rule is pi over 3 plus some multiple of 2 pi, or I can call that theta 1. My other general rule is 2 pi over 3 plus 2 pi k. So in this particular problem, there are two general rules that will give me infinitely many solutions. Okay? Now the question is, now here's where it gets interesting. I want you to find 6 actual solutions. So before I do that, I just want you to see that if I'm going to plug in a whole bunch of different numbers for k to crank out 6 distinct solutions, I want to make these a little bit easier to deal with. So I know that 2 pi, in terms of a fraction with 3 in the denominator, so 2 pi, if I want 3 to be in the denominator, would be 6 pi over 3. Okay, so I'm going to rewrite this just for the sake of doing some work one time instead of doing it multiple times. I'm going to rewrite this general rule as pi over 3 plus 6 pi over 3 k. So that as I plug in numbers for k, I already have a common denominator. Now, do you have to do this? Of course not. I like to do this so that when I start cranking these out, the pattern is a little bit cleaner to see. Same thing with this rule. 6 pi over 3 k. Now, once again, you don't have to do that. I like to do that. Okay, so we've already found the general formula, the general rule that will generate all solutions. Every single solution is one of these two values where k is any whole number or its opposite, an integer. So let's crank out these 6 solutions. So first I'm going to plug in 0. Well, if k is 0, this whole value is 0. So one of my solutions is simply pi over 3 plus 0, or pi over 3. If k is 1, then I get pi over 3 plus 6 pi over 3 times 1. So 6 pi over 3 plus 1 pi over 3, 7 pi over 3. That's a second solution. Let's see what happens when k is 2. Get pi over 3 plus 6 pi over 3 times 2. So this is going to give me 12 pi over 3 plus 1 pi over 3, which is 13 pi over 3. Okay? Now you can generate, if it just says find 6 solutions, you can just continue using only the one general rule. It doesn't say use one general rule to generate 3 solutions and the other general rule to generate 3 more. It just says find 6 solutions. So I'm going to, you could continue, but I want to find, a few from each. So if k is 0, I get one solution that's just 2 pi over 3. Okay, k is 1. I get 2 pi over 3 plus 6 pi over 3 times 1. Ooh. So I get 6 pi over 3 plus 2 pi over 3, which is 8 pi over 3. Let me just draw your attention to the fact we are now finding angles that are larger than 2 pi. For one, just to show you that those solutions exist, there are infinitely many solutions, the vast majority of which are greater than 2 pi. Matter of fact, all of them are greater than 2 pi except for these two in the positive direction. And then plug in 2. My battery is dying. So 2 pi over 3 plus 6 pi over 3 times 2. So 12 pi over 3 plus 2 pi over 3, 14 pi over 3. Bam! So we now have 6 distinct solutions, and in this case there were 2 general rules. So once again, nothing really new. We're just expanding it a bit for better understanding, for deeper understanding. All right, one more example. All right, same directions as the last problem. Build a general formula or general formulas, general rules so that you can find all solutions, and then list 6 specific solutions. Now, if this were cosine of theta, pretty quick and easy like the last problem, but we see cosine of 3 theta. So just to kind of show us kind of the logic again, what argument, what value for cosine is going to give me out root 2 over 2? So we make a little rough sketch. Root 2 over 2. For cosine, remember cosine, those are my x-coordinates. My x-coordinates need to be positive. I need to get root 2 over 2. There are 2 angles at which that happens. One of those angles is pi over 4. First quadrant, very few mistakes with that angle. But the second one is at 7 pi over 4. That's where mistakes happen. So be careful there. So here's where I start. I know that 3 theta will either equal pi over 4, don't forget your plus 2 pi k, or 3 theta will equal 7 pi over 4 plus 2 pi k. So 2 general rules. But once again, I have to solve for theta. So I'm going to divide everything in both equations by 3. So theta will either equal pi over 4 divided by 3, pi over 12. And then this is 2 pi over 3k. Okay, so theta will either equal this as a general rule, or theta will equal that. You can go with this, or you can go with that. Middle school flashbacks, y'all. All right, so there it is. Those are my 2 general rules. But now I need to crank out some solutions. So at this point, not a lot going on other than a lot of arithmetic. Now, once again, I'm going to go ahead and circle my general rules. So this is part of my solution. Those are my general rules. Now I'm going to do like I did last time. If I want a common denominator, so I have pi over 12 and 7 pi over 12, then I'm going to multiply top and bottom by 4. And that's going to give me 8 pi over 12. Okay, once again, you don't have to do that. I like to do that arithmetic one time and then crank out a bunch of different solutions. Once again, you don't have to do that. All I did was multiply the numerator by 4 and the denominator by 4 to change the general rule so that the k term has a common denominator. So that these 2 terms have a common denominator. So I'm now going to find 6 specific solutions by cranking them out. So let's plug in 0. When I plug in 0 for k, k term is gone. So one solution, plug in 0 for k, 7 pi over 12. Boom. Now I'm going to plug in 1. So I get pi over 12 plus 8 pi over 12 times 1, which is just 8 pi over 12. Same thing over here. 7 pi over 12 plus, if k is 1, that's just 8 pi over 12. So that gives me 7 plus 8, 15 pi over 12. Always reduce if possible. 5 pi over 4. This gives me 9 pi over 12. Always reduce. 3 pi over 4. Actually, I shouldn't say reduce the fraction. All the workshops I've been to in the last few years say that's bad because it makes it sound like you're actually making it a lesser value, and you're not. You're just simplifying the fraction. So I'm not reducing the fraction. I am simplifying the fraction. That's all right. So now, when k is 2, I get pi over 12 plus 8 pi over 12 times 2. It's going to give me 16 pi over 12 plus 1 pi over 12. 17 pi over 12. Okay, same thing over here. So I start with 7 pi over 12 plus 8 pi over 12 times 2. So 7 pi over 12 plus 16 pi over 12, 23 pi. 23 pi over 12. My video maker does not want to finish this video. Okay, so my hope is you've seen through these 4 examples that solving trig equations takes a little bit more than what we've done in the past. Definitely unit circle, but at this point you really want to stop and make sure that you're paying attention to the directions, because the directions will be mixed up at this point. You might only build a general rule. You might only find 4 specific solutions. You might find 6 solutions. You might only find solutions between 0 and 2 pi. So at this point, you know what to do. You just got to be careful and abide by the directions. That is video 2 on solving trig equations. All right, good luck. Keep practicing, and I will see you all in class or at tutorial.